Welcome back to Math 104. We are looking at the event O intersect N complement. Once we've understood what this event is, we'll be able to find its probability, describe it in words, and find another way to write it in set notation. First, what is this event? This event is the complement of something. The something is O intersect N. So whatever O intersect N is, this overlap region, the O negative donors, O intersect N complement is everything else. That means that we should shade everywhere outside the O intersect N region, everywhere. The only thing left unshaded at the end of this process is O intersect N itself. What's the probability of this event, O intersect N complements, everything outside O intersect N? We have two choices. One is to notice that O intersect N complement, our event, consists of 1, 2, 3 basic regions. Therefore, the probability of O intersect N complement is the sum of the probabilities associated with those 3 basic regions, and that comes out to be 0.93. But there's another way, and actually an easier way, which is to notice that the probability of not being O negative equals 1 minus the probability of being O negative. What is this event in words? It is the event that the donor has a blood type other than O negative. How else can we write our event in set notation? One approach would be to look at the 3 basic regions comprising O intersect N complements and take the union of them. So we could take O intersect N complement, union with O complement intersect N, union with O complement intersect N complement. If that's the answer you wrote, that is fantastic. But I'd like to propose another approach that I don't expect you to have thought up on your own. Let me write it down and then try to convince you that it's true. Let's think about what this means. O complement, union, N complement. O complement is a certain event, and we can shade it in the diagram. Right, I'm going to shade it in orange here. Everything outside of O is the event O complement. N complement is another event. I can shade it. That is, I can shade everywhere outside of N. Everywhere outside of N. Now let's look at O complement, union, N complement. Think which basic regions have received orange shading or blue shading or both. Right here we have blue shading, here we have orange shading, and here we have both. So O complement, union, N complement consists of all the basic regions that have blue shading or orange shading or both, and lo and behold, those are exactly the same 3 basic regions as in our original event that's shaded here in black. That's enough right there to argue that these really are the same event. To pull together what we have done so far, the following laws are useful for understanding events built up from complicated combinations of unions, complements, and intersections. De Morgan's laws state that for any events, E and F, the complement of the union equals the intersection of the individual complements, and the complement of the intersection equals the union of the complements. That might look intimidating. How are you supposed to remember this? Here's the way to think of it. The way to simplify a long complement sign over something more complicated than just a single letter event is that in the simplification, the individual events get complement signs, but, this is really important, the union gets flipped into an intersection. Similarly, in the other law, the intersection gets flipped into a union. Think of this as converting a long complement sign over a complicated event into short complement signs over simpler events at the expense of remembering to flip unions to intersections and intersections to unions. We have certainly spent some productive time talking about 2-circle Venn diagrams. And if you like 2-circle Venn diagrams, you're going to love 3-circle Venn diagrams. Here is one. Let's notice some things about its structure. There is indeed an overlap region contained inside all 3 circles. So death to humans is what is common to zombies, robots, and aliens. But there is also a region here that is common to zombies and robots. It's inside the zombie circle and inside the robot circle, but outside the alien circle, and that is no emotions. There are 3 such regions, because for each one of our circles, there's going to be a basic region outside it that is inside the other 2 circles. Once again, we have basic regions that are inside one circle but outside the others, and once again we have a basic region that is outside all 3 circles. Just to be clear, that is a box containing all 3 circles, and in order to do this correctly, you must draw that box. What kinds of problems can we solve with 3 circle Venn diagrams? Let's look at one. Among the students taking a certain Rutgers course, 1 student is selected at random. So that's our experiment. The course has a roster, there is some list of students enrolled in the course, and we select one at random. The outcomes in this experiment are equally likely. Let's consider the following events. The event C, that the selected student lives on campus, the event J, that the selected student is a junior, and the event H, that the selected student is a history major. Suppose there are 1,000 students taking this course. Nice round number. That will make the probability computations pretty easy. Of these 1,000 students taking the course, 600 live on campus, 200 are juniors, 100 are history majors, 90 are juniors living on campus, 50 are history majors living on campus, 60 are junior history majors, and 20 are in all 3 categories. So our first task is to draw a Venn diagram, and we could fill in probabilities, but just for variety, let's fill in the number of students corresponding to each basic region of the diagram. Now, how do we even begin? We have to look through the information that's given and try to see, is there any piece of information here that corresponds to one single basic region? Yes, it's the 20 students who are in all 3 categories. That is the only number that we're given that corresponds to a single basic region of the diagram. These 60 juniors who are history majors are spread across 2 basic regions that are inside the J circle and inside the H circle, depending on whether they live on campus or not. The 50 campus-dwelling history majors are spread out over these 2 basic regions of the Venn diagram. Of the history majors who live on campus, some are juniors and some are not juniors. The 90 juniors living on campus are spread across these 2 basic regions of the Venn diagram. Some of them are history majors, the rest are not history majors. Similarly, the 100 history majors are spread across all 4 basic regions inside the H circle. The 200 juniors are spread across all 4 basic regions inside the J circle, and the 600 students living on campus are spread out across the 4 basic regions inside the C circle. We must not forget the outside region, which will contain any student who falls outside of all 3 of these categories. So who is in all 3 of these categories? That's 20 students. They live right in the middle here. We work our way outward and look at the juniors who live on campus, of whom there are 90 in total, 20 of whom have already been accounted for. That leaves 90 minus 20, that is 70, who are in this basic region. Juniors who live on campus but are not majoring in history. Then we have 50 history majors living on campus, 20 of whom have already been accounted for, leaving 30 in this region. We've got 60 junior history majors. Of the 60 juniors majoring in history, 20 have been accounted for who live on campus. The other 40 out of those 60 live off campus. The rest involves a little more computing, but it's not so bad. There are 600 students living on campus. We have accounted for 120 of them across 3 basic regions. That leaves 600 minus 120, which is 480 students who live on campus, but they're not juniors and they're not history majors. Similarly, there are 200 juniors total. 130 have been accounted for. That leaves 70 juniors who live off campus and are not history majors. There are 100 history majors total, 90 of whom have already been accounted for. That leaves just 10 who are not juniors and are not living on campus. Finally, we have to address the fact that there is this outside region. We are told that there are 1,000 students total in the sample space, 1,000 students total who are taking the course. Every student has to appear in one basic region. Those 1,000 students minus the number already accounted for, which turns out to be 720 when you add them all up, gives us 280 students who are living off campus, they're not majoring in history, and they are not juniors. Just to point out, a quicker way to add up this 720, you don't need to add up these 4 separate numbers again because you already know that the entire on-campus circle contains 600 students. So you can start with that 600 and then just add 70 plus 40 plus 10 to get up to 720 students already accounted for. Having done all that work, now we can get to the probability questions. We can ask, what is the probability that a randomly selected student lives on campus or is a history major or both? It is a very good idea to start out shading the Venn diagram. To count towards the event that we're looking at, a student would need to live on campus or be a history major or both. Anyone inside the on-campus circle is contributing towards the likelihood of this event. Anyone inside the history major circle is contributing towards this event. If the student happens to be a campus-dwelling history major, that's fine too. We have already shaded that region. Thus, there are 6 basic regions. Out of the 8 basic regions total, there are 6 basic regions that are in this event, and the total number of students there adds up to 650 out of 1,000 total. That gives us a probability of 0.65. Again, this addition is a lot quicker when you realize that the entire C circle is being counted, and you already know that there are 600 students total in the C circle. So you just have to add up 600 plus 40 plus 10. To describe this event in set notation, now students sometimes find this a little hard to believe, but here it is, C union H, that's it. C union H. It's all the students in C or in H or in both who are being counted. That is exactly what we mean by C union H. Now you're thinking, wait a minute, don't we have to say something about J because J is one of the circles in our diagram? Good question. The answer is that the event contained no mention of J, so you are not obligated to mention J in your set notation. Someone else who's watching this video right now is thinking, well, what if we took the union of all 6 of these basic regions? Could we write it that way? Yes, you could, but that'll get rather complicated, and C union H really is much simpler. Before going on to the next video, find the probability that a randomly selected student is not a history major who lives on campus. Think a little bit about that event. Not a history major who lives on campus. And find the probability that a randomly selected student is a junior who lives off campus and is not majoring in history. This one also requires you to think a bit about what the event actually is.